Alright, in this video we'll be applying both of Kirchhoff's laws. So let's say we have a circuit like so, where we have a 6 volt power supply, let's say, and we have a circuit that comes down here. We have a 3 ohm resistor over here, circuit comes back up, and we have a 2 ohm resistor over here, okay, 2 ohms. And this is going to be a parallel circuit where we have another power supply right here, and let's say this is 2 volts, and we have another 5 ohm resistor right here. So what I want to find is the current that is coming out of the power supply, so we can call this I1, the current that is coming into our first branch, and the current that is going in to our second branch, okay? And so, like I said in my current law video, Kirchhoff's current law states that all currents leaving a node is equal to 0, okay? As you can see, we have defined I2 and I3 to be leaving the node, and I1 to be entering the node, okay? And so if a current is entering a node, that's just the negative of it leaving the node. And so what we will have is negative I1 plus I2 plus I3 is equal to 0, and therefore I2 plus I3 is equal to I1. Alright, and if we want, we can rewrite that as I1 is equal to I2 plus I3. Alright, so they're all in order, okay? So now that we've used Kirchhoff's current law to define our currents, we can now use Kirchhoff's voltage law to find out the values of those currents, okay? And so like I said in my voltage video, Kirchhoff's voltage law states that the algebraic sum of all voltage rises around a loop in a circuit equals 0, okay? And so as you can see, we have 3 options for our closed loop. We have this loop right here, we also have another loop over here, and we also have this entire loop right here. Okay, now for this question, we only need to apply 2 loops in order to solve it. So we will apply these 2 loops right here. Okay, as we start from our starting point and go around the loop, we can see that we have a 6 volt rise over here. So we can go loop 1, and that's a 6 volt rise to start off with. And then as you can see, as the current goes through here, we can see we have a voltage drop over here. Now, as we know, V is equal to IR. We know the current going through this resistor is I2, and the resistance is 3 ohms, and so therefore the voltage is going to be equal to 3I2. And as this is a voltage drop, therefore this is minus 3I2. As the charge continues to flow up here, we know that this current is equal to I1 because of Kirchhoff's current law, okay? And so therefore the voltage drop across here is going to be equal to 2I1, and so therefore we can minus 2I1 over here, and this all equals to 0. Now, as you can tell from this equation, we have 2 unknowns, and therefore we need to form another equation in order to form simultaneous equations so we can solve this, okay? And so that second equation is going to come from the second loop right here. We can start with a 2 volt rise right over here, okay? So this is loop 2 now, and we start with a 2 volt rise. As the current moves through here, we can see we have another voltage drop, and this is still equal to 3I2, okay? So it's the same situation we had over here. And so our loop continues down here. However, we run into a bit of a problem. The problem is that we've defined I3 to going this way, okay? However, we are coming down this way. And so if I3 is coming up here, we are going to have a voltage drop in this direction, okay? And so this voltage drop is going to be 5I3. However, because in our loop we're coming through in this direction, we can say that this is equal to negative 5I3. Notice how the voltage arrow has now changed direction, okay? And so therefore, we can say that this is minus negative 5I3, and so therefore this is the same as saying plus 5I3. And that's all equal to 0. Now, as you can see, we have 2 equations right here. However, one thing that you might have noticed is that we've introduced another unknown. And so therefore, now that we have introduced 3 unknowns, we need a 3rd equation in order to solve this. The good thing is that we have defined Kirchhoff's current law as before, okay? And so we can use this in our equation. So we know that I1 is equal to I2 plus I3. And so therefore, we can substitute this into here. And we get this equation is equal to 6 minus 3I2 minus 2I2 plus I3. And so therefore, simplifying this, we get 6 minus 3I2 minus 2I2 minus 2I3. And so therefore, 6 minus 5I2 minus 2I3 is all equal to 0. And this is all equal to 0 also, okay? And so therefore, now we have two equations with two unknowns on both equations, and therefore now we can use simultaneous equations. Okay, so now we have 6 minus 5i2 minus 2i3, and that's all equal to 0. And we have 2 minus 3i2 plus 5i3, and that's all equal to 0 also. What we can do is times this top equation by 3 and times this bottom equation by 5. And what that will do is make our two I2 expressions equal to each other, and so therefore we can cancel them out. And so therefore we get 18 minus 15I2 minus 6I3, and that's all equal to 0. And we get 10 minus 15I2 plus 25I3, and that's all equal to 0 also. Another thing you could have done is made our I3s equal, and in order to do that, you need to times this top one by 5 and this bottom one by 2. Okay, so either or would have worked. So now we can minus these equations off of each other, and we get 8 minus 31I3 is equal to 0, and so therefore 8 is equal to 31I3, and we get 8 all over 31 is equal to I3, and this gives the value of I3 as 0.258 amps. There we go. Alright, so now that we've found the value of I3, we can now plug it into any one of these equations and find the value of I2. And so therefore, 6 minus 5I2 minus 2 times I3, which is 8 over 31, okay, using the fraction to keep whole values, and that's all equal to 0. And so therefore we can say 6 minus 5 times I2 minus 16 all over 31 is equal to 0. 6 minus 16 over 31 is equal to 5.48 minus 5i2, and that's all equal to 0. 5.48 is equal to 5i2, and so therefore 5.48 all over 5 is equal to i2, and this gives a value of i2 as 1.097 amps. There we go. Or we could say that this is 34 all over 31 amps in order to keep whole values for future calculations, okay? And so now that we have the value of I3 and the value of I2, we can now find the value of I1 using this equation right here. And so therefore, I1 is equal to I2, which is 8 over 31, so 8 all over 31, plus I3, which we just found as 34 all over 31, so 34 all over 31. And so therefore, I1 is equal to 42 all over 31, or we can say this is equal to 1.35 amps. There we go. There is another way in which we can solve this problem. This method is what I learned in my first year of engineering, doing an electrical engineering course. Okay, so if you don't quite understand this, don't worry about it. It's from university, so all good. But this method is definitely faster, and so if you can get a grip of this, then you'll be sweet. So this method, we still use our Kirchhoff current law, okay? So let's redefine this and say this is I1 right here, okay? Notice that's just the exact same thing, but we're just flipping the sign, okay? And so therefore, I1 plus I2 plus I3 is all equal to 0, okay? Remember, our Kirchhoff's current law states that the sum of all currents leaving a node equals 0. Now, if we were to define the voltage across here as V, okay, and because we know that V is equal to IR, and therefore I is equal to V all over R, because we've defined this as V, and our resistor that our voltage is measuring over is 3 ohms, we can say that I2 is equal to V all over 3. And so we can write that in, V all over 3. Okay, but what about I1 and I3? Well, we can see here that this point is still part of the same node as this point, okay? And so the voltage across here must still be V, okay? However, if we track I1, it goes through and over here, okay, by our definition. As you can see, this voltage goes across a 2 ohm resistor, and so therefore we would have V all over 2. Now notice something, we have a 6 volt power supply, and what this power supply means is that each coulomb of charge over here has 6 volts less energy than each coulomb of charge over here, okay? So as the charges go across, they gain 6 joules of energy. And so if we're measuring everything in terms of this reference voltage, this voltage right here is going to be V minus 6. And remember, V is this reference voltage right here, okay? You can pause the video and have a think about why that is right now. And so therefore, I1 is equal to V minus 6 all over 2. And we can move this to make it look nicer. And so we run a similar process for I3 also. We can see that I3 goes through a 5 ohm resistor, but also passes through a 2 volt source. And so therefore I3 is going to be V minus 2 all over 5, and that's all equal to 0. And so now we can solve for this voltage across this 3 ohm resistor right here, okay, this V value. And so therefore we get V all over 2 minus 6 all over 2 plus V all over 3 plus V all over 5 minus 2 all over 5, and that's equal to 0. We get V multiplied by half plus 1 over 3 plus 1 over 5 minus 6 all over 2 minus 2 over 5, and that's all equal to 0. V multiplied by half multiplied by a third multiplied by a fifth is equal to 6 over 2 plus 2 over 5. This simplifies to 17 all over 5, and we can carry this down over here, okay? And so therefore V is equal to 17 all over 5 divided by half plus 1/3 plus 1/5, and this gives a voltage of 3.29 volts. Okay, and so therefore, because we know this reference voltage now, because we found all the currents in terms of this reference voltage, we can find I1 is equal to our reference voltage minus 6 all over 2, and so that's equal to 3.29 minus 6 all over 2, and so that's equal to negative 1.35 amps. And as you can see, that is the exact same value that we found here. Now notice the signs being different because in this scenario we defined I1 to be coming downwards. However, in this scenario, we defined I1 to be going up, okay? And so in reality, I1 is actually going down like this, okay? And we can do the same process to find I2, and that's equal to V all over 3, and so that's 3.29 all over 3, and that's equal to 1.097 amps. And as you can see, that is the exact same value that we had over here, okay? And so therefore I3 is equal to V minus 2 all over 5, and so that's equal to 3.29 minus 2 all over 5, and that's equal to 0.258 amps. And as you can see, that is the exact value that we found previously, okay? So in my opinion, this method is much quicker. However, if you don't understand it, all good, you can certainly pass and get excellence using this method right here, okay? And so that's applying both of Kirchhoff's laws in NCEA level 3. See ya.